Good morning. This is another lesson for Honors Pre-Calc. This is your second set of notes on limits. This is evaluating limits analytically, which means we're going to do some things algebraically and look at some properties for limits. So I mentioned this in the first lesson about limits. The first thing you should do on any limit question is you should plug in the number. If x is approaching a number c, go ahead and plug that number c into the function. And if it actually gives you a number, that is the limit. This is called direct substitution. That's what you should try first on every single limit problem. Just plug in the number, see if it gives you a value, and if it does, that's going to be your limit. Now, not all functions are going to be that easy. If a function works this way, it's called well-behaved, and it's going to be continuous at c. So basically what you're going to see is you're going to see a function at c. It's just going to be continuous there. There's not going to be any jumps or gaps or holes or anything like that. Now, we're going to look at some basic properties for limits, some real simple stuff. Now, we're going to let b and c be real numbers. So when you see b, that's a constant. When you see c, that's a constant. When you see x, that's a variable. N is going to be some positive number, okay? And again, some positive integers, so no decimals, no fractions, anything like that. If you let x approach c for a constant, the limit of a constant is the constant itself. So if you take the limit as x approaches 4 for 6, y equals 6 is just a horizontal line. It always equals 6, so the limit has to be 6. The limit of a constant is the constant itself. This is real simple. As x approaches c of x, you just plug in the number. You get c. So what's the limit as x approaches 4 of 4? We're following direct substitution up here. Plug in the 4. The limit is 4. The great thing about having a variable to a nice round integer exponent, not negative exponents, just positive exponents, positive integers. If you have x to the n and you've got the limit as x approaches c, the answer is going to be c to the n. So an example of this, if the limit as x approaches 4 for x squared, just plug in the 4. The answer is 4 squared, which is 16. Now, let's show some other properties of limits here at the bottom of the page. And if these aren't making sense again, pause the video, send me a text message, let me know what you need. If you have a constant times a function, and the limit of that function is L, you can take b times L. Now, what the heck does that mean? This is 6 times x squared. Remember up here, the limit as x approaches 4 of x squared was 16? Well, look, the only difference between that and this is I threw in the multiplication by 6. So you can literally take 6 times the limit of x squared, 6 times 16. So my limit here would be 96. If you add functions or even subtract functions, you can add or subtract their limits. So the limit of 6x squared we just found out was 96. The limit of x up here as x approaches 4 would be 4. So we can take 96 plus 4. It's 100. You're going to see in a lot of these problems I'm using limits we've used previously on the page, and maybe a few new ones. If you multiply functions, you can multiply their limits. So the limit of f is L, the limit of g is k. You can take L times k. Well, over here, if I take x squared times radical x, what was the limit of x squared up here? It was 16. What's the limit of radical x as x approaches 4? Well, it's the square root of 4. Direct substitution, that would be 2. 16 times 2 is 32. Seems pretty simple so far. It's the same for division so long as k does not approach 0. The limit is f. If f is divided by g, that would be L divided by k. So over here, 6x squared approached 96. We just saw radical x, take the square root of 4, that approaches 2. You can just divide those limits so long as that bottom doesn't approach 0. That would give me 48. Same thing with powers. If you take a function to a power, you can take the limit to that power. So we know the limit of x squared was 16. If I take that function and raise it to the third, I can take its limit and raise it to the third. That would be 4,096. So these seem like some pretty simple ideas when it comes to limits. When you add functions, you add their limits. When you subtract functions, you subtract their limits. You multiply the limits. Divide the limits. And you know we can't divide by 0, so we're not going to do that here either. And if you take a function to a power, you can take its limit to a power. Those are some of the simple ideas we've presented on this page. Let me jump to the next page here. A lot of these are very simple properties, so if any of them, again, aren't making sense, stop the video and give me a holler. Polynomial functions and rational expressions. The great thing about those two functions, if you have a polynomial, you can just plug in the number. That's what this means. If you see a polynomial function like x squared plus 3x plus 2, you just plug in the number. That's what I'm doing right here. The limit as x approaches 2, this is a polynomial. Just plug in the 2. 2 cubed is 8. 2 times 2 is 4. Minus 4, the limit is 8. Same thing here. This is another polynomial function. Plug in 2. You get 2 to the 5th, which is 32, plus 4 gives me 36. So polynomial functions is very simple to find the limit. Just plug in the number. Rational expressions, it's the same thing so long as the bottom does not approach 0 when you plug in c. You can take the top and plug in the numbers, take the bottom, plug in the numbers. So I took that polynomial divided by that polynomial to create a rational expression. That's what a rational expression is. It's a polynomial divided by a polynomial. You guys should remember that from the first part of the year. If I plug 2 into the top, we already know we'd get 8. If I plug 2 in the bottom, we already know from the previous work I'd get 36. This reduces to 2/9. So the great thing about polynomials and rational expressions, so long as it doesn't make the bottom equal to 0, we can just plug in the numbers. Now we have to be careful with radicals. And I hope you guys can read my work here. Odd roots always work, because if I let x approach 27, I can just plug in the number. Take the cube root of 27, it's 3. If x approaches negative 27, I can plug that in. I can take the cube root of negative 27. That does give me negative 3. Now it's even roots, we have to be really careful. If I plug in 16, the fourth root of 16 is 2. Again, I can take the fourth root of the limit. The limit as x approaches 16 is 16. The fourth root of 16 is 2. Now, if x is approaching negative 16, this function does not even exist at negative 16. So we say this limit does not exist. The function doesn't even exist there. So we've got to be really careful when we use even roots. Composite functions, it's simply a matter of plugging in numbers. This function right here is a composite. It is a composite of a radical and a polynomial. It's this polynomial plugged into that radical. Well, if I let x approach 4 on this composite function, I always plug it into the inside first. So we're going to plug 4 into x squared. That gives me 16 plus 9 is 25. And then what I'm going to do is I'm going to let x approach 25 and take the square root of 25, which is 5. All of that work is essentially what we did up here with a composite function. Again, really what this rule comes down to, if you can plug in the number and you can find a numerical value for what the limit is approaching, that is going to be your limit. So even with composites, you can just plug in the number. Just make sure you evaluate it correctly. Plug it on the inside, then take the outside function. Trigonometric functions. The limits of trigonometric functions depend on their domains. And it might be harder to see. I'll zoom in here a little bit. You'll notice with sine and cosine, the domain is all real numbers. You can plug anything into sine and cosine. But we just talked about this at the end of the year here. What's the domain of tangent? X cannot equal pi over 2 plus pi k, because that's where tangent has asymptotes. So if it's anything other than this, you can find the limit just by plugging in the numbers. It's the same thing with cotangent. Cotangent has asymptotes at x equals pi k. So you cannot use x equals pi k, like pi, 2 pi, 3 pi, negative pi. You can't find the limits there, because those are asymptotes. But we can find the limit anywhere else. Secant is pi over 2 plus pi k. Cosecant is pi k. Remember those. K is an element of the integers. Remember those domains. So when we look at these problems down here with sine, if I let x approach pi over 4, I can just plug it in. What is sine of pi over 4? Thinking of our unit circle, it's radical 2 over 2. The limit is x approaches negative pi over 6. I'm just going to take cosine of negative pi over 6. Look at your unit circle. Be radical 3 over 2. The limit as x approaches 0. Can I find tangent of 0? Yes. It doesn't satisfy that set of asymptotes there. It is in the domain, so what is tangent of 0? It is 0. Doing a couple more trigonometric functions over here. Let x approach 0. Can I plug in cotangent of 0? No. No. 0 is an integer. 0 times pi is 0. Cotangent has an asymptote there. Now, what happens along asymptotes? Asymptotes, on one side or the other, they go to infinity or negative infinity. With cotangent at 0, it goes to infinity on the right, negative infinity on the left. So what we're going to say here is it does not exist because it's unbounded. Remember in the previous lesson, if you've got infinities, you're going to say it does not exist, especially if it goes in opposite directions. This is what happens at 0. There is an asymptote, and on this side it goes up, and on this side it goes down. It doesn't approach the same thing on both sides. Okay, sorry you can't see that. It doesn't approach the same thing on both sides, so I've got to say it just does not exist, it's unbounded. Now what about secant of pi? Well, that's 1 over cosine of pi, and cosine of pi is -1. Again, unit circle stuff. Secant of pi is -1. As x approaches 5 pi over 3 of cosecant of x, I just take cosecant of 5 pi over 3. Use your unit circle. That's 1 over sine of 5 pi over 3. And sine is negative radical 3 over 2, so this would be -2 radical 3 over 3. I'm going to zoom back out here so we can see some more of my notes. I am going to right now, and I'm probably going to come back to this, I'm going to skip some of the trig that we're talking about right here, and I'm going to go to a different section of these notes. We'll come back to that page on trig. Don't worry, we'll come back to it. We're going to do some strategies for solving limits by hand. To solve these limits by hand, we're going to do several things. We're going to divide out like fractions, so basically factor and cancel. We're going to rationalize. That is what we're going to use with radicals. We're going to talk about the squeeze theorem or the sandwich theorem, and also we're going to do some common denominator stuff toward the end of the lesson. Now, you'll notice this first problem at the bottom here. This is a rational expression. It is a polynomial over a polynomial. If I plug 1 into the bottom, I get 0. So I can't just plug in the number. In fact, if I plug 1 into the top, I'd get 1 plus 3 minus 4. I'd get 0 over 0. This limit starts out as an indeterminate form. It is 0 over 0. We can't do this limit the way it's written. Now, that doesn't mean it's undefined. It doesn't mean it does not exist. What we're going to do is we're going to factor and cancel. So if I factor that top, it factors into x minus 1, x plus 4. And the x minus 1 on the top and the bottom are going to cancel, which is great for us. Because if I plug in 1, that's the 0 over 0 right there. That's what we're trying to do. We're trying to cancel out that 0 over 0. In fact, that's a big hint. If x is approaching 1 and you get 0 over 0, there is probably an x minus 1 as a factor on the top and the bottom. And once those factors cancel, you can plug in the 1. 1 plus 4 is 5. The limit here is 5. There is no value at x equals 1, but on the left and the right, I can guarantee you if you graph that function correctly, you will see on each side it approaches 5. Now, what about this next one? If I put in 2, the top's going to be 0, the bottom's going to be 0. Again, this is an indeterminate form. We do not say it does not exist. We say we need to try something else. So factor it. If x approaches 2, I can guarantee you there's an x minus 2 top and bottom. 99% of the time, I can guarantee you that's what's going on. Those x minus 2s are going to cancel. I can plug in the 2 now. I get 2 plus 2, which is 4. There's my limit. Now, some problems are a little bit harder to do than others. You guys may have to go back to some of the units we did at the beginning of the year where we talked about factoring. This is a sum of perfect cubes. Now remember, the sum of perfect cubes, if it's a cubed plus b cubed, this is a cubed plus 2 cubed, would be a plus b times a squared minus ab plus b squared. If that was a minus sign, that would be a minus. These would both be plus. In fact, this works for higher powers as well. I don't know if you guys remember me talking about this, but if it's a plus b, it's going to be a plus b to start. Watch the pattern. A squared, a to the first, a to the 0. B squared, b to the first, b to the 0. Do you guys remember this? If it's a to the 5th and b to the 5th, it starts out a plus b. A to the 4th, a to the 3rd, a squared, a to the first, a to the 0. Go backwards. B to the fourth, B to the third, B to the second, B to the first, B to the zero. If it's plus, they alternate. If it's minus, they're all plus. That works for any odd powers in factoring. So how does this sum of cubes factor? Well, it's x cubed plus 2 cubed. This is x cubed plus 2 cubed. So the first factor on the bottom would be x plus 2, and it would go x squared, x to the first, x to the 0. 2 squared, 2 to the first, 2 to the 0. That's plus. These alternate. Some review on factoring there. Look again. If x approaches negative 2, remember what I said. There's the 0 over 0. In fact, I should have done that first. I should have plugged in negative 2. I get 0 on the top. If I plug in negative 2 on the bottom, I'm also going to get 0. So this was a 0 over 0 problem again. That's why I went into the factoring. I should have plugged in the number first. But look, negative 2 plus 2 is 0. Negative 2 plus 2 is 0. I have canceled out the 0 over 0. Plug in negative 2 to the bottom. I get 4 plus 4 plus 4. My answer is 1/12. Now, you see some other work here that I put down. This is just showing you again, if you don't remember how to factor, you can use synthetic division. If x is approaching negative 2, put negative 2 out front, and that's x cubed plus 0x squared plus 0x plus 8. Do your synthetic division. Drop the 1, multiply, add those numbers. Multiply again, add those numbers. Multiply again, add those numbers. The remainder is 0. Why is that? Because x plus 2 is a factor of the bottom. And here's the other factor. X squared minus 2x plus 4. So there's a couple ways you can figure out how to factor these. Now, how did I know to use the negative 2? Remember again, I'm telling you right now, this works 99% of the time, if not all the time, with problems you're going to see. If you plug in negative 2 and you get 0 over 0, I can almost guarantee you x plus 2 is a factor on the top and the bottom. Give it a try. Again, mark this page. We're coming back to that trig in a little bit. Hope you guys can read the top of this page here. Sorry it's in red. If you've printed out your notes, you should be able to see it. I've got x to the 5th minus 1 over x minus 1. If I plug in 1, again, that's going to be an indeterminate form. It's 0 over 0. So how am I going to factor this? Well, if x is approaching 1, I told you, I can almost guarantee there's an x minus 1 on the top. This is a difference of fifth powers. So how does it work? X minus 1 is the first factor. X to the fourth, x to the third, x squared, x to the first, x to the 0. 1 to the 5th, 1 to the 4th, 1 to the 4th, 1 to the 3rd, 1 to the 2nd, 1 to the 1st, 1 to the 0. If that's minus, these are all plus. Just showed you that on the previous page. Follow the formula. Or you could do synthetic division to figure out that remaining factor. Just put a 1 out front. The x minus 1s cancel. Why is that good for me? That's the 0 over 0 canceling out. And if I plug in 1s now, I'm going to get 1 to the 4th plus 1 cubed plus 1 squared plus 1 to the 1st plus 1. Gives me 5. So even though I got an indeterminate form to start, that doesn't mean I can't find my limit. Now, what about the next problem? If you plug in 2, I guarantee you here, the top's going to be 0, the bottom's going to be 0. Feel free to pause the video for a second, plug those numbers in. You're going to see the top is 0, the bottom is 0. That's going to be 8 plus 4, which is 12, minus 2 minus 10, which is minus 12. They cancel out, give me 0. The bottom, if I plug in 2, I get 4 minus 6 plus 2. That's 0. Now, because x is approaching 2, ladies and gentlemen, I can almost guarantee you x minus 2 is a factor. Sure enough, x minus 2 times x minus 1 is how the bottom factors. Now, how did I figure out the top? I did synthetic division. X cubed plus x squared minus x minus 10. If x is approaching 2, put a 2 out front. Remember how to do synthetic division. Drop the 1, multiply, add. Multiply the 2 and the 3, put the 6 there, add the column. Multiply the 2 and the 5, put the 10 there, add the column. What's my remaining factor? X squared plus 3x plus 5. There it is. The x minus 2's cancel. Now plug in your 2. If I plug in my 2, I'll get 15 on the top, I'll get 1 on the bottom. There's my limit. Now, I hope the factoring and canceling was making sense. Yes, you are going to have to go back and possibly look back to your lessons in the first part of the year on factoring. Now, the second type of problem we're going to work with here is rationalizing. When does rationalizing come into play? Rationalizing comes into play when you have radicals, and it doesn't matter if the radical's on the top or the bottom. We're still going to rationalize. Now, when is this useful? Remember, the first thing you're supposed to do is plug in the number. If I plug in the 1 here, I'd get 1 minus 1 over 1 minus 1. That again gives me 0 over 0. That, ladies and gentlemen, is an indeterminate form. So what am I supposed to do? Just quit? Say it doesn't exist? No. What you're going to do is you're going to rationalize. Now, where's the radical in this problem? The radical is on the top. Don't start thinking, hey, I've got to get rid of radicals on the bottom. That's not the idea here. My final answer will work on that. Here, what you're going to do, whenever you see the radical, this is a radical minus 1. So I'm going to multiply by its conjugate, top and bottom. Radical x plus 1, top and bottom, because that equals 1. Now, do not multiply the bottom out here. Leave it alone. Only multiply the conjugates in these problems. What's so great about conjugates? When you FOIL, you don't have to worry about the outer and the inner terms. Just multiply the first terms. What's radical x times radical x? That's x. What's negative 1 times 1? It's minus 1. Why don't I have to do the outer and inner terms? Because the outer terms would give me positive radical x. The inner terms would give me minus radical x. Those cancel. Now, just like before when we factored in canceled, we are trying to get rid of the 0 over 0. Look here. 1 minus 1, 1 minus 1. If I were to plug in the 1, that's my 0 over 0 that's canceling right now. I'm left with nothing on the top but a 1. On the bottom, I'm left with radical x plus 1. I can plug in the 1 now. Look, whenever you cancel everything, remember you put a 1. Okay? So I can just plug in the 1 and I get my answer. It's 1/2. So again, even though we got a 0 over 0 in indeterminate form, that does not mean we can't do the limit. Same thing on this next problem. If you plug in 1, you'd get 0 on the top. The bottom, 10 minus 1 is 9. Radical 9 is 3. 3 minus 3 is 0. Oh my goodness. Another indeterminate form. So what am I supposed to do? You're going to multiply by the conjugate. Where's my radical this time? My radical is on the bottom. Multiply by its conjugate. Radical minus 3, so I'm going to multiply by radical plus 3. And again, I do not want you to multiply the other part out here. These are not conjugates. Don't multiply them out. The x minus 1 on the top and the conjugate, leave it alone. Hopefully you can see that in the blue there. On the bottom, I would get 10 minus x from these two terms. And negative 3 times 3 is negative 9. Now, I know it might be hard to see in my work here, but pay close attention. I'd have a negative x, and 10 minus 9 would be 1. I have 1 minus x. And some people in my previous classes are thinking, oh, crap, we're stuck. No, we're not. 1 minus x right there. Everybody see the 1 minus x? That's the opposite of x minus 1. Look, x, negative x. Negative 1, positive 1. Those are opposites. So you can cancel those and leave me with a negative 1 times that conjugate on the top. And guess what? You just canceled the 0 over 0. 1 minus 1 is 0. 1 minus 1 is 0. We just canceled out the 0 over 0. So the negative out front is from that negative 1, and I plugged in the 1. That'd be radical 9, which is 3. 3 plus 3 is 6. My answer is negative 6. So watch out for those factors that are opposites on these that can still cancel. Again, if you're struggling with this, if you need a second to write some things down or to look at your notes closer, don't be afraid to just pause the video. X approaches 4. What's 4 squared? 16. 16 plus 20 is 36. Square root of 36 is 6. 6 minus 6, 0 on the top. Plug in 4 in the bottom, I'll get 16 minus 16 again. I got 0 over 0. Now, multiply by the conjugate. This is 6 minus the radical. So I'm going to multiply by 6 plus the radical, top and bottom. Why, again, am I doing top and bottom? Because that equals 1, and I'm not changing my value. Do not multiply out anything but the conjugates. The bottom I'm going to leave alone. There's a reason for that. On the top, I get 6 times 6, which is 36, minus whatever the result I get from the radicals. If I multiply these radicals together, I get x squared plus 20. But a negative times a positive, I have to subtract that amount. So there's a negative x squared right there. And 36 minus that 20 would be 16. So the top is 16 minus x squared. Remember again, that's the opposite of the bottom. So when I canceled out that 16 minus x squared and that x squared minus 16, I got a negative 1 on the top. That's where this negative 1 comes from. On the bottom, I'm left with 6 plus radical x squared, so that would be 4 squared plus 20. Evaluate all of this. 4 squared is 16, plus 20 is 36, square root of 36 is 6, 6 plus 6, 12. My result is negative 1 over 12. And I hope you're getting the hint on how these radical problems work out. Now, I threw in this next problem with my calculus class just to see if I could fool them. Because if you plug 2 into the top, this is the square root of 4, which is 2. This is 6 minus 2, which is the square root of 4, which is 2. 2 minus 2 is 0. Ah, crap. Wait a minute. I'm allowed to get a 0 on the top. Let's see what happens on the bottom. Plug in 2. This would be the square root of 10 minus 1, which is 9. Square root of 9 is 3. That says plus. So I plug in the 2. 4 times 2 is 9 plus 1. 4 times 2 is 8 plus 1 is 9. Square root of 9 is 3. I get 3 plus 3. That's 6. Wait a minute. That's not an indeterminate form. I know what 0 divided by 6 is. It's 0. So every once in a while, people get the idea, hey, I've got to factor and cancel. Hey, I've got to rationalize every single time. No, you don't. What's the first thing we said about evaluating a limit? You plug in the numbers to see if it works. 0 over 6 is not an indeterminate form. Try it on your calculator. It will say 0. If you type 0 divided by 0 on your calculator, it'll say there's an error. It's indeterminate. Now, the squeeze theorem, let's talk about this shortly, and there'll be a problem later on where I'll show you how this works. The squeeze theorem works very simply. If you have a function g that is approaching L, and you have a function h that's approaching L, and f has to stay somewhere between them. So if f has to stay between them, it's logical just because of this funneling system, it squeezes it. You can see it squeezes, and f also has to approach L. Now, perfect example of this. We know, you should know, we talked about this with sine of x. The largest sine of x can get on a unit circle is 1. The smallest sine of x can get on a unit circle is negative 1. Now, watch this. I'm going to divide everything by x. Negative 1 over x. If you let x approach infinity, what is negative 1 over infinity? It's hard to think about, isn't it? But negative 1 over 10 is 0.1. Negative 1 over 100 is negative 0.01. Negative 1 over 1,000 is negative 0.001. The bigger I make the bottom of a fraction, the smaller the fraction gets. So if I let the bottom approach infinity, this fraction is going to approach 0. This fraction, 1 over infinity, if I let that bottom get bigger and bigger and bigger and bigger, that whole fraction gets smaller and smaller and smaller, and it approaches 0. Now, wait a minute. If this approaches 0 and this approaches 0, then any function that's in between them, that's less than or equal to that function and has to be greater than or equal to that function. If that approaches 0 and that approaches 0, the inside function has to approach 0 at all, as well. The limit as x approaches infinity of sine of x over x. That approaches 0. And don't get that confused. Before we talked about the limit as x approached 0 of sine of x over x. That approached 1. They're different limits because this one goes to infinity, this one goes to 0. So be careful with that. But that's how the squeeze theorem works. Now, we are going to go back, not to the next page, because if you guys take a look at the next page, and let me pull it up here for you. The next page, we start talking about trigonometry again. So what I'm going to do is I'm going to go back to this third page of your notes. Okay? Right in the middle of the page, it talks about trig. Remember, we did this in the first lesson. I showed you graphically. I showed you with the table. The limit as x approaches 0 of sine of x over x is 1. The limit as x approaches 0 of 1 minus cosine of x over x it approaches 0. So what do I do when I start seeing trigonometric problems that involve some of these types of situations? You'll notice here the limit as x approaches 0 of sine to the 6th x over x to the 6th. What's the limit of that? Well, the top is sine to the 6th, the bottom is x to the 6th, so it makes sense. This is sine of x over x all raised to the 6th. Now, what's the limit as x approaches 0 of sine of x over x? Well, that's 1. So I can take the limit which approaches 1 here and raise it to the 6th. 1 to the 6th is 1. Well, that seemed pretty simple. Okay. Now, what about tangent of x over x? Well, tangent, if I plug in 0, this would be 0 over 0. Tangent of 0 is 0, and then there's a 0 on the bottom. This is an indeterminate form, so I got to try something else. Well, what's tangent? Tangent is sine of x over cosine of x. And that's all divided by this x on the bottom. Now, if you remember, if there's an x on the bottom, and it's below a fraction, if I have a fraction divided by another fraction, I would multiply by the reciprocal of the bottom. So this x would end up on the bottom of the top. It would be sine of x over x cosine of x. Everybody see that sine of x over x? What does that approach? That sine of x over x, that approaches 1. Well, what am I supposed to do with the cosine? Plug in the 0. What is cosine of 0? Holy crap, that's 1. So the 1 in the blue here represents the sine of x over x. That's what it approaches. That cosine of x, which also cosine of 0, which approaches 1, is on the bottom. 1 times 1, the limit is 1. And I have let my classes in the past use this as another formula. The limit as x approaches 0 of tangent of x over x. We just proved that approaches 1. Okay? Now, what about secant? This secant problem has bothered people. If you plug in 0, secant of 0 is 1, 1 minus 1 is 0. And on the bottom, 0 times anything is 0. So this is a 0 over 0 problem. It does not mean that this doesn't exist. Remember, secant is 1 over cosine. So I rewrote this in purple here, and I hope you guys can read it. It's 1 over cosine minus 1, and the bottom is x times 1 over cosine. Now, I do not like having fractions within fractions, and we learned how to do this when we dealt with fractions before. Multiply by the common denominator. The common denominator is cosine. Cosine of x times that, the cosines would cancel and give me 1. Cosine times minus 1 is minus cosine. On the bottom, the cosines would cancel and just leave me with x. Hey, that is my formula. This approaches 0. So you can see how some of these trig problems work out. Now I'm going to make it a little bit harder. We're going to jump back a couple of pages. Okay. Find where it says the special trigonometric limits again. I wrote them on this page so they were in front of you. And I'm going to also write this one. The limit as x approaches 0 of tangent of x over x, that also approaches 1. We just proved that on the previous page. Now, my calculus kids catch on pretty quickly to some of these. The first one they wanted to do on this page, and I'm going to do it as well. Look at this bottom problem. Sine to the 7th x over x to the 7th. That is literally sine of x over x to the 7th. That's the same as the problem we did on the previous page. Sine of x over x approaches 1. 1 to the 7th is 1. So long as those two exponents on the top and the bottom match, it's going to equal 1. Now, the other thing I will do is I will ask my classes on this first problem here, if it's sine of 5x over 3x, take a wild guess what you think that limit is. And this is what everybody says. They say 5/3. That's one of the most common answers. The answer is 5/3. Now let me show you why. I'm going to multiply the top by 5, and I'm going to multiply the bottom by 5. Now what is 5 over 5? It's just 1. Why did I do that? I pulled that 3 out front, and I left